Here. All right. Okay, so we're back. Hopefully everyone can hear me. I am not muted. Okay. All right. Cool. Okay, so we kind of left off with this question last time. Want to hear some thoughts on what do you think this guy converges to? So last time we spoke about the radius of convergence and the interval of convergence of a power series. Power series was just a fancy way of writing an infinite polynomial, right? Polynomial of infinite degree. We looked at where this polynomial would converge. That is, what are the set of x values that I can plug into this polynomial, and the infinite list of numbers would actually converge to something meaningful, to a real number. We found the radius of convergence and interval of convergence of three guys last time, one of which was this guy. And we found that his interval of convergence was the open interval from -1 to 1. So if I wrote this guy out, you'll notice this looks like 1 plus x squared plus x cubed plus x to the fourth plus ... going on forever. And this will add up to something meaningful as long as I plug in values for x that are strictly between -1 and 1. And the question is, what does that actually add up to? We know it converges, but it turns out we can tell what it converges to. Any ideas here? Boris, how did you know that? What's your reasoning? Yeah, you can turn on your audio if you want and just chime in. Hello?
Hello.
Yeah, what's your reasoning for your answer?
I saw a rule somewhere.
Oh, you saw it? You didn't figure it out? Did anyone figure it out who hasn't seen it before?
I mean, would the 1 over 1 minus x be, like, just working off of the 1 over 1 minus x, would you just rewrite the series as a different series in order to be able to solve it, or?
No, it's pretty much in a nice form, and I think Jhevon is actually right. Yeah, so Jhevon and Sean are seeing it. It's actually a geometric series, right? Notice it has a pattern. It kind of looks like if you take a(r) to the n goes from 0 to infinity, and you set a equals 1 and r equals x, you actually end up with that guy. And we know that this guy converges when your r is less than 1 in absolute values, and it converges to a over 1 minus r. If absolute value of r is less than 1. So, yeah, this guy actually adds up to, because it's a geometric series, a over 1 minus r. It adds up to 1 over 1 minus x. Now, that is interesting because it's a geometric series, so a couple of people saw that. Notice that what's happening, you started with a number and you kept multiplying by the same number for each term. 1 times x is x times x is x squared times x is x cubed, etc. You keep multiplying by the same thing. This is the common ratio. X is your common ratio. It's actually geometric. And we actually proved this was like another way of showing when the geometric series converges. But we get that. So one thing I want you to appreciate here, what we're going to dive a little bit more into today, but we'll actually get way more into it the next lecture, is this guy's a function, 1 over 1 minus x. I can think of that as a function. So I can think of my f of x, some function is 1 over 1 minus x, and in fact we kind of know what that function looks like. When x is 1, you have an asymptote. And it's going to look like 1 over x, but it's flipped because the x is negative, so the right side is in the bottom, and the left side is on top. So that's that guy. And basically what we're saying is that this is equal to 1 plus x squared plus x cubed plus dot dot dot, as long as our x, if absolute value of x is less than 1. And basically what that means is that if I look between -1 and 1, I would have, strictly speaking, so if I open up a hole here and just actually draw this part of the curve here, another way to think of this part of the graph is this infinite polynomial. I can actually express this function as an infinite polynomial, as a power series. And that's actually going to be pretty useful as you can probably start imagining. So one, the polynomial version, yes, it's infinite, but it's actually a nice thing to work with. If I wanted to, for example, start differentiating and integrating this guy, I can actually do that pretty easily using the power rule. Whereas this guy is going to need a chain rule and all sorts of things. Like computationally, this guy is very nice to deal with. The polynomial is a very nice version to have things in. So in other words, I want you to kind of start getting the appreciation that power series, once I think of my x as a real variable, you can almost think of them as representing certain functions. And we're going to talk about how well they can do this in the coming up. What? I'm not sure what you mean by that, but getting more complex. But yeah, so this function I can think of as this series as long as I'm within this window. That's the name of the game. And what I want to do now is I want us to figure out one way to actually do this for other functions. How can we come up with power series for some other functions? Now one way to do this is to actually use a known power series in order to help you develop the power series of some other function that you don't know about. So what I want us to do here is find power series representations for, we're going to do 3 examples. So I'm making all of them somewhat similar because they're all connected in a special way. So copy that down. We're actually going to go through these 3 examples. And it's going to kind of lead us into nicely into the next topic. Okay, so you can copy that down, take a screenshot or something. Now we just started looking at power series last time, so pretty much all we know is the definition. And yes, we know about one power series, the series of x to the n. So basically what we're going to do here is using known power series. And in that regard, there's not much to go on. We really only know about one power series specifically at this point. At least what function it adds up to. So that being said, let's actually do that for this one. 1 over 3 plus x. Okay, ideas on how to actually figure out a power series for that guy.
Pull out a -3 from the denominator, and you'll still have the form of.
Why would you pull out a -3?
Well, I mean, based on what we did earlier, I'm assuming we're looking for the form of 1 over 1 minus x in some way, shape, or form.
Yep.
And if you pull out the -3 from the denominator, you can pull out a constant fraction, -1 over 3 times 1 over 1 minus x.
No, here you'd have -1 minus x over 3.
Oh.
You get a negative in front of there. So yeah, no. Because we'd mess up the pattern there. I think pulling out the 3 is a good first move to make, but I would pull out a positive 3 actually. But yes, you're trying to make it look like a pattern that you've seen before, namely the one that we started the class with, but that requires that this sign here be a negative. Ideas on how to get that to happen? Legally, right?
Minus -x over 3.
Right, write it as a negative of a negative. So I have 1/3 times this guy. And now what? Anyone see what to do now? Because we know about 1 over 1 minus x, that's going to give us the series n goes from 0 to infinity of x to the n.
A third times the series of -x over 3 quantity to the power of n from 0 to infinity.
Right. So here, it's like you have this 1 over 1 minus x, and then you just take the x to the n. In the same way, it's like we have 1 over 1 minus this guy, which I think of as the x, and I just put that guy to the n. Yeah, that's a way to actually translate to the series. In fact, let's clean this guy up a little bit. So this is 1/3. I can have the series n goes from 0 to infinity. I can distribute the n. I will get -1 to the n, x to the n over 3 to the n. And in fact, I can actually let's move that 3 inside. So the 3 can come inside because we know we can factor constants in and out of series. That was a property of series. And we have that. And that's our guy. This is actually equal to the function 1 over 3 plus x. So by knowing about one power series, one option I have is if I have something, I can manipulate that function to look like one side of a known series equation that I have, and that way develop a power series for some other random function. So knowing 1 over 1 minus x gives me a series. I can use that knowledge to figure out this guy as a series, namely he's going to be this series. Now you might wonder, where does this work? And again, you know that your 1 over 1 minus x works when your x, quote unquote, is less than 1 in absolute value. Well, in this situation, your x is minus x over 3. So we just need minus x over 3 to be less than 1 in absolute values. which means your x should be strictly less than 3 in absolute values. So this is going to work on the interval -3 less than x less than 3. So I can represent this guy as an infinite polynomial on this region over here. Within this window, I can essentially think of this function as this series. It's they'll actually exactly the same, they're equivalent. Me plugging in an x value over here is the same as me plugging in an x value over there, as long as the x values I'm plugging in fall within that window. Now, once I'm outside this window, what's going to happen is this series is going to diverge. In fact, you should probably be able to tell that if once I'm outside that window, say I plug in x equals 4, for example, the test for divergence here is going to give us that this diverges, because that limit is going to go to infinity. But yeah, so that's one way we can write this function as a series. Any questions on this one? Let's try the second one. Ideas here. ln what? How would we use ln here?
If you take the derivative of the previous equation, then you get the negative of this one.
Right, so this one is actually connected to the first function via a derivative. Now, there's another connection that I want to point out. So, one way to look at this probably would be the first guess for a lot of people. It's actually just square it. They would think of this as, well, this is 1 over 3 plus x times 1 over 3 plus x. It's just the square of what I had before. And I know how to write each of these as a series. Right, so this is minus 1 to the n, x to the n over 3 to the n plus 1. And this is minus 1 to the n, x to the n over 3 to the n plus 1. And so now the question is, how do you get that written as a series? Now, you could actually get that done, but this is actually not easy to do. So you might recall that the product of series is not the series of the product. This actually means you'd have to multiply an infinite number of things times an infinite number of things, group-like terms. It's actually going to be very difficult to actually multiply out these guys directly. So thinking of this as literally a square is probably not the way you'd want to go, because multiplying two series is very, very hard in general. At least it's just, most of the time it's not worth the computational power to figure it out. One thing you could notice though is that, yeah, if I have something like 1 over x, how can I connect it to something that looks like 1 over x squared? Well, one connection is to actually use the derivative. So if I differentiate, then this would actually give me the negative of 1 over x squared. And that's a much nicer connection to make here, because when it comes to series, we kind of know how to do the derivative. You just differentiate the polynomial version. So, yeah, that was the connection. First thing you want to notice here the easiest thing to notice is that this is actually the negative derivative of this function. And I know what this function is. So this is the negative derivative of that series. Okay, how do I differentiate this series?
You can just switch derivative with the sum sign.
So you want to distribute the derivative?
Yeah.
So in other words, you think the derivative of the sum is the sum of the derivatives. Now, in general, that would be fine, but we are dealing with an infinite sum here. So how do you know that's actually okay? How is that legit?
Why don't we just expand it and differentiate the expansion?
That's what this is saying. This is actually saying exactly the same thing.
Oh, okay.
You want to expand this and then put the derivative on each thing, right? Well, then that would give you a sum of the derivative of each one of these elements here. But there's actually a concern here. How do we know that this can be done for an infinite number of terms? Let's see who's been paying attention here. This was actually a concern that was brought up a couple weeks ago. Why is that allowed?
It converges absolutely.
Because it converges absolutely. So remember, there's something that was called the rearrangement theorem. And the rearrangement theorem basically says, if you have an infinite sum that converges conditionally, then by rearranging the terms, you can actually get a different answer. So you distributing a derivative over a conditionally convergent thing or a divergent thing actually doesn't make any sense. You'll get a different answer if you took the derivatives in different orders, which shouldn't happen, or you shouldn't want that to happen. So it turns out the ability to switch the series and the derivative sign, or to do calculus across a sum like you would normally want, we need absolute convergence. So this is only legal. We can do this because of absolute convergence. How do I know that we have absolute convergence? Well, we use the ratio test to derive the formula for this series. The ratio test, whenever it shows convergence, shows absolute convergence. So we do have, this series does converge to the function 1 over 3 plus x. It does so absolutely, because the ratio test was how we actually proved that. So this is actually allowed. And so we just want to differentiate. This is what's going to call differentiate term by term differentiation, which basically means distribute the derivative across the infinite sum. It's only legal if you have an absolutely convergent infinite sum. Okay, so now that being said, what is the derivative of this thing?
You can just leave the negative 1 to the n over 3 to the n plus 1 alone and differentiate x to the n.
Right, so this part here, the negative 1 to the n over 3 to the n plus 1, the derivative actually thinks of that as a constant because it's d dx, it's the derivative with respect to x, which means n is a constant. N is actually just an integer that's being counted by the series. As far as the derivative is concerned, this part here is a constant. So how do you differentiate a constant times a function? Well, you leave the constant alone, differentiate the function. So now all I have to worry about is differentiating the x to the n, which that's a rule, right? So that's like the power rule for derivatives. Just bring the n down, n x to the n minus 1. So the derivative of this is going to look like minus 1 to the n, n x to the n minus 1 over the 3n plus 1. And I can bring this minus 1 inside. And so that would become minus 1 to the n plus 1 times n x to the n minus 1. And that is a way that we can think about this function, 1 over 3 plus x squared. Now right now we're just actually playing the game of using a formula to our advantage here and differentiating the formula. But you're going to, later on I'm going to show you some benefits of actually thinking of this function in such a form. But for now, that's how you would actually get it done. One other thing that you might notice here, well, let's not, we'll do that later. Let's not get ahead of ourselves. So, one connection between this and the guy we had before was a derivative. It's just a negative derivative. So we have the negative derivative of this series because we know that's this series. And then, how do we actually find the derivative of this infinite sum? Well, it's the sum of the derivatives of the infinite sum because we have absolute convergence. If we did not have that, right here we're stuck, we're dead for it. This would actually not even make sense in general. It would be meaningful in some convergence sense, but that would require that we don't change the order of anybody. So because we have absolute convergence, this function is that no matter what order I add these guys in, I can distribute and the commutativity rule still works. And so this, we get this. We differentiate that using just the power rule because this is a constant, the x is the only variable with respect to the derivative, and we get this guy. So there was a minus 1 on the outside that I moved in, multiply the minus 1 to the n, gives me the minus 1 to the n plus 1. That's our series. Okay. So give you some time to copy that or take a snapshot or whatever. Yeah, I think we're making good, we're keeping a good pace here. Let's do the third one, which after seeing how the second one works out, how the third one is going to work out would probably be a little bit more straightforward for people to see. So let's say I had f of x equals ln of 3 plus x. So maybe someone besides Zekwin wants to chime in on this one. Can you see a connection that you can exploit?
Can you take the derivative of ln and make it like 1 over 3 plus x?
So the derivative of ln of 3 plus x is 1 over 3 plus x. That's actually true. If I plug in the series here though, how does that actually help me?
Integrate the series from there?
You integrate the series. So it's probably nicer for me to think of the ln as the integral of that as opposed to the derivative of this. Because I don't have a derivative sign here. So I in fact want to think the opposite. Just think of this as the integral of 1 over 3 plus x dx. And then I'm just thinking now of integrating the series. Because as far as I'm concerned, this guy is that series within a certain window, right? Once my x is between minus 3 and 3, this is doable. Now again, because of absolute convergence, I'm allowed to think of the integral of the series as the series of integrals. The integral of the sum is just the sum of these integrals. And how do I integrate that then?
Can you do the same thing too, like factoring the constant out of the integral
Yeah.
and integrating it to the end?
Integral of x to the n is? What's the integral of x to the n?
X to the n plus 1 over n.
And x to the n plus 1 over n plus 1, right? So leave this alone, then just change this to x to the n plus 1 over n plus 1. So I'm going to have minus 1 to the n, x to the n plus 1 over n plus 1. But then I still have that 3n plus 1 right here. Now we're forgetting something. This is an indefinite integral. Right, so we actually do still need a plus c. Now, you don't really have to think about this, but in future classes this might be a thing that you'd have to worry about. But what you can think of this as, this is just an infinite number of terms that you're distributing the integrals across each term. You get a plus c for each of them. So this is really just a series of c1 plus c2 for each term. But we're just saying that that adds up. Just think of that as adding up to one other series here, which we're calling C as the answer. So we're going to assume that series converges. Because we know that it actually will work out here because our original series converges absolutely. So you integrate. It's an indefinite integral, so there's a plus C. So there's a little bit of work we have to do now here. It turns out that we don't fully have this answer with that plus c here. So one way you can figure out what that plus c would have to be is you can actually figure it out, is you just plug in a convenient x value in both sides of the equation. I know that ln of 3 plus x is equal to this thing, so maybe I can plug in something convenient. That is going to allow me to figure out what this c is. Can we think of something convenient to plug in here for x? Three. So someone thinks 3 is what we should plug in. So here's what would happen if I plug in x equals 3. Well, these guys are going to cancel, which, yeah, that kind of looks nice. But now I'm going to have C as this sum. Right, so if I plug in x equals 3, I would have ln of 6 is equal to the alternating harmonic plus C. Which, that's fine technically, but there's something nicer that you could plug in here. Well, I wouldn't go with -3, but 0, as Boris said, is a good thing. Because if I plug in 0 for x, I just have the series of zeros. I'm adding 0 an infinite number of times. That's actually something that I know right off the bat what that is. I can plug in x equals 0. This would mean that ln of 3, because I plug in x equals 0, is equal to, well, now the series disappears because my x equals 0 is equal to c, which is left over here. And so what I'd be able to say is that ln of 3 plus x is equal to C, which is ln of 3, plus this series. I can write this as minus 1 to the n over n plus 1 times x over 3 to the n plus 1. So that's the series form of this guy. Not as clean as the other one. We have this constant lingering here, but it's still a series of terms. Now, in future classes, you can think of this as the n equals minus 1 term. That's a whole other story because logarithms and yeah, it's a whole other story. Let's not worry about it. But this is a way that I would express this guy as a series. It's an infinite sum plus ln 3. And what I did here was, because the x to the n plus 1 and I had 3 to the n plus 1, I just put both under the n plus 1 power and divide them here. Just make it look a little bit nicer. And I'm left with the minus 1 to the n over n plus 1 goes here. So that is a series version. So 0 was a very convenient x value to plug in there. And we have that. So get myself out of the way here so you guys can copy or take a screenshot or whatever. Now here's something cool. I'm actually going to use this to figure something else out. Something that I mentioned before. And you probably wondered, well, that was weird. Where did that come from? Here's something cool. Let's go back to that whole x equals 3 business. Now, what redeemed? Yes, Boris. Now, here's something cool. Let's use this known equation here and actually plug in that x equals 3. What would happen? I would have, oh, that was just someone chiming in. I would have ln of 6, because I'm plugging in x equals 3, equals ln of 3 plus, now if I plug in x equals 3 here, that just gives me 1 to the n plus 1, which is just 1. I would have that, which, notice I can have here ln of 6 minus ln of 3 is equal to this guy. Now ln of 6 minus ln of 3, that's actually just ln of 2. I know that's actually just ln of 2 because ln of something minus something is ln of the division. So ln of 6 minus ln of 2 is ln of 6 divided by 3. ln of 6 minus ln of 3 is ln of 6 divided by 3, which is ln of 2. I mean, some of you have probably seen it. I mentioned something in passing. I don't even know if you guys remember. But yeah, let me actually multiply both sides by a -1. I just want that so that this power is the same as that. So minus 1 to the n plus 1. You can in fact notice that I can think of this guy as the same as n goes from 1 to infinity. That's just by me shifting indexes. Right. If you write these out, you'll notice that they'll give you the same thing. This one starts at 0, but I reduced all the n's by 1, and they're started at 1. It's going to give me the same values. And we get this. So a while back I told you about the value of two series. I told you that the sum of 1 over n squared, n goes from 1 to infinity, is actually pi squared over 6, which was very weird. And the next thing I told you guys was, oh, the alternating harmonic converges conditionally, and in fact it converges to minus ln of 2, which might have also seemed very weird at the time. But that's how it happened. So one of the reasons why the kind of manipulations we've been doing in this example, there are many other reasons, but one of the reasons is it allows us a way of actually computing values of series if we just notice a connection with some other series that we know adds up to. Now finding what a series specifically adds up to is very difficult in general, so this actually is a technique that can be used. I now know that the alternating harmonic adds up to minus ln of 2. In fact, this is basically saying if I take minus 1 plus a half, minus a third plus a fourth, minus a fifth, plus dot dot dot, that all adds up to minus ln of 2, which is, might seem very strange, but we actually just justified it. It actually is a consequence of us being able to express 1 over 1 minus x as a geometric series, which is, yeah, pretty cool, right? So,
Since it converges to 1,
come again?
since it converges conditionally, does it mean that we can rearrange the terms and make it, like, not make it minus ln2?
Yes, correct. It is minus ln2 provided I maintain the same order right here. So this is the convergence is conditional here. One thing you can also notice is that the original series that we used to actually manipulate to get this, it actually did not work at 3 specifically. At least it did not work absolutely at x equals 3. However, the only reason why I was allowed to plug in x equals 3 here is because by doing the integration, my denominator changed that allowed me to use the alternating series test to show convergence. If you actually compare the series where I wasn't allowed to plug in 3 to this one, you'll notice that the reason why I'm allowed to plug in 3 here is because my denominator actually changed to something where the alternating series test would work, where it wouldn't have worked before. But yeah, so we have conditional convergence here. This is a conditional convergence series because if we put absolute values around all the terms, it's harmonic, so it does not converge with absolute values. So yes, this is a conditional convergence here. Converges conditionally. But yeah, I just thought that was cool. We still don't know enough to prove that the sum of 1 over n squared is pi squared over 6. You'll probably do that in another class. We're not going to be able to do that here. There are calculus ways to do it, but probably the nicest way is to use a double integral, which you're not going to see that until Calc 3. So after you do Calc 3 and you learn about double integrals, if your teacher doesn't talk about it, you can come back, oh, I know about double integrals now. Can you show me why the sum of 1 over n squared is pi squared over 6? And at that point, I'll be able to show you. We're not really going to see any methods here where we can prove that, though. But yeah, pretty cool. I know that the alternating harmonic adds up to minus ln of 2. And I just used a geometric series to figure that out. Pretty cool. Here is another use of series. Computing difficult integrals, some which would be literally impossible to compute in elementary functions. So, for example, let's say I wanted to compute this integral here. The integral from 0 to 1 of x over 1 plus x to the 9th. Okay, so you can copy that down. That's our next challenge. We are going to actually do this integral. Now, in some sense, this integral is not that bad, actually. You can actually integrate this, but you wouldn't want to. So some of you might just say, oh, well, we should be able to integrate this guy, you know, using some sort of clever substitution. It's really going to be, it's really harder than you think it is. And, you know, just find the antiderivative of this, plug in 1 and plug in 0, and subtract them. Fundamental theorem of calculus. If you were to plug in the indefinite integral of that guy into Wolfram alpha, you're going to start to realize that, yeah, this guy probably isn't as easy as I think. It's the answer, the antiderivative of this is huge. And I plugged the same guy into Symbolab, and it couldn't even come up with an answer. It literally ran out of computing time. And it's like, yeah, our system can't handle this integral. So yeah, it's a really nasty integral. It's doable. But yeah, you probably wouldn't want to have to do it directly. However, we're going to use series to do this guy, and it's actually not going to be that bad using series. So yeah, that's the next challenge. So the first thing is, what we're going to do is try to write this guy as a series. And we are going to want to integrate that series, kind of how we were integrating before, assuming that we'll have absolute convergence. So that is going to be the first step. That's the first thing we're going to do. So now I throw the ball to you guys. How would you actually express this as a series? Ideas?
If you pull out the x, can you use the 1? So we were always looking for the form of 1 minus, or 1 over 1 minus x, right?
Right, so by doing that, we get the 1 on top.
Yeah, and then you have minus negative x to the 9.
Okay.
And then you can represent the right side as a power series and integrate the two separately.
No, so that's where you messed up just now.
Oh.
Messed up just now. So this is minus x to the 9th to the n. How do you do with that? The integral of x times this. Because the integral of a product is not the product of integrals. Huh?
What's the reverse product rule? I forgot.
Integration by parts?
Yeah.
You want to do integration by parts of the series? There's an easier way.
Yeah.
Anyone see a nicer way to deal with that? Nope. Maybe write it not as a product somehow. It's doable.
I don't know, make it like 1 over x to the 9 over n. Never mind.
The series deals with n as the variable. There's a hint.
Does the series count as a constant in this case? No, right?
No, the ends are constant. As far as the integral is concerned, the ends are constants. As far as the series is concerned, the x's are constants. Does that help? We need a face emoji there. It's like how is showing a face. Constant times a series. What are some things we're allowed to do? Yes, you can distribute the x, or more, one way you can think of that is to multiply the x in. The x is a constant as far as the series is concerned. I can move it inside and outside the series at will. So I would have minus 1 to the n, x to the 9n, but then I multiply that x in, so it becomes 9n plus 1. So yeah, we have absolute convergence here, so that's a sum that I can do mathematical operations with. Distributive law is going to work, commutativity of addition is going to work. Just multiply the x in. That just means move the x inside the series. I would end up with this guy. Then, again, because of absolute convergence, so this is really a series property here. I can move the x inside. Then by absolute convergence, I can switch the summation and the integral. The integral of the sum is going to be the sum of the integrals. And then continuing that over here, it's just the power rule again. So this is a constant, that add 1 to the power, divide by the new power. So this is going to be minus 1 to the n, x to the 9n plus 2 divided by 9n plus 2. And that's going to work between 0 and 1. I'm going to plug in 1 for x. And then plug in 0 for x, and I get that. That's the answer to this integral. So this is the series form of the answer, right? Now, this may or may not be useful to you, but that is the answer. That is the integral. And trust me, it's a lot. What we did is a lot easier than it would be for you to use one of the techniques that I taught you in the beginning of this class. Wait, did someone ask a question? Oh, the explanation for distributing the x is because we had a property. A constant times a series is the same as I can move the constant in. This was a property of series that we had covered. One of two algebraic properties. Constants can go in and multiply the thing that's inside. And according to the series is changing the ends. So the x, from this perspective of the series, the x is a constant. So I can move it inside because of this property here.
But how did you get -1 to the end? That's where I was lost.
Oh, I distributed the powers. You have minus x to the 9th to the n to the minus 1, and there. That's the distributive law. ab to the n is a to the n, b to the n. So it's minus 1 times x to the 9th, raise the minus 1 to the n, and then raise the x to the 9th to the n. So this is just a property of exponents. I can separate these guys. That's the answer. Now, you might be wondering, how is that actually useful? Now this is useful in a couple ways. You might say, I don't even know what that's going to add up to. Especially with an integral on the other side of that equation, that's going to be hard. However, you might notice that this is an alternating series, and we actually know how to approximate alternating series. We have the alternating series approximation theorem. So you might say, well, I don't know a closed form for the answer. When you have a nice compact form that is not an infinite sum, it's an elementary function, you call that a closed form answer. So here we don't have a closed form answer. We have an infinite series answer. But if you wanted the answer to say 5 decimal places, you can get that to 5 decimal places. So you might say, we can approximate this, you should know. To any desired accuracy. Right? So one thing you can just notice, the alternating series approximation theorem tells us the n plus first term tells you how close you are to the actual answer. So if you have a tolerance of, say, k, like someone says, I want the error to be 0.001. I want to be 3 decimal places accurate or 2 decimal places accurate. What you can do is you can just set the n plus first term, 1 over 9 times n plus 1 plus 2, set that less than k, solve for n. Then sum that many terms. In fact, if you were to type the definite integral into something like Wolfram alpha, this is probably the way that it would have done it. So Wolfram alpha is going to compute something and is going to pop up a decimal on the screen saying, hey, this is the answer to that integral. What it actually did was converted it to a series. It'll recognize that it's an alternating series. Then it knows it wants to display 15 decimal places. It is just going to set k equals 0.000, 14 zeros and a 1. Solve this for n. You'll get some large number, but it's a computer. It loves adding up a bunch of numbers. And it'll just add up a bunch of numbers and then spit that answer out on the screen. And so a lot of these computer algebra systems, they attack it from the series point of view. But when they pop up an answer on the screen, it's really an approximation because they're just giving you some finite number of decimals, right? Wolfram alpha is going to give you, what, somewhere between 6 and 15 decimal places at any given time, unless you get a paid version and ask it for more. But yeah, it can get the answer to within any desired accuracy you want. So the series version, for all practical purposes, the series answer is pretty much as good as the nice version of the answer. Which again, if you wanted to plug that in Wolfram alpha, I'm not sure if it will actually give you the nice version, but the indefinite integral as an indicator of how messy that would be should let you guys know. You can actually try to type the indefinite integral of x over 1 plus x to the 9th in Wolfram alpha. You'll see how much of a mess it is. It's the series way of getting to the answer was actually a lot nicer. So this is another way in which series can be very useful when it comes to computing difficult integrals. Some of them would even be impossible, and we'll do some of those next class actually. Where it's literally impossible for you to write out the answer by hand. You can get a series version of the answer and then just approximate that to within any accuracy that you want. And yeah, your problem is solved in every practical way. So yeah, that's another cool thing for series. Six decimal places is all pro membership gets you. Yeah, so that's even nicer. Like it probably won't have to add up too many terms. But now you can yes, that says tolerance. So in order for Wolfram alpha to give you the 6 decimal places here, which someone computed is 0.439285, what it would have done is it would set k equals 0.0000001, solve for n, it will then add up that many terms of this. So So it'll plug in n equals 0, then n equals 1, then n equals 2, then n equals 3. Add up all those numbers, and it's going to boop, pop out the decimal value of the answer to 6 decimal places. And it's a computer, it can do this very quickly. But that's the inner working. That's how it's that's how it would do it. So when you ask a computer for a numerical answer, most of the time series is the way it's going to get there. It's a very efficient method, and you don't need any fancy techniques from calculus. You just write it as an infinite polynomial. The calculus part is super easy in that situation, and then when you get a series answer, just approximate it. It's pretty cool. At least I think so. Yeah. But we did it by hand. Look, Ma, no hands, no computers. That's the answer. But this actually raises another question. What if the thing I'm looking at, I can't see a way of connecting it to 1 over 1 minus x? What if it was like an integral maybe of, say, sine of x cubed? How am I going to find a relationship between this and that? Like, what would I have to come up with in order to get this guy as a series, in order to do something like what I did before? And the question now is there a way to create power series in general? Is there a way to create power series in general? Now, someone who's seen all the things that I just showed you might very well wonder that thing. They'll say, yeah, it's nice if I'm looking at something that I can think of as 1 over 1 minus x, but what if I'm not? Is there any hope? I give you a random function. Could you come up with a power series for it? Whether or not you have a series that you already know about looking kind of like that guy, or its derivative or its integral looks like the series that you know about, without that being the case, could you actually come up with a power series in general? And unfortunately the answer is no, that's all we have. I'm kidding, no, of course. The answer is yes. With restrictions, of course, there is no free lunch. And that's what I want to talk about now. How can we create power series in general? Right? I give you a random function. Under what conditions can I create a power series with that function, whether or not I know some other power series that looks like it already? So here's what we're going to do. A lot of times you want to invent something, you kind of, well, yeah, I mean, if it doesn't, if the series we're looking at doesn't converge, and we kind of want absolute convergence, so yeah, so given a function, is there a way to come up with some absolutely convergent series that I can use to represent the function, is the question. Then we'll also deal with the question of how well would the series actually represent the function? On what window will it represent it? Or how close to the function is the series? Can we think of them as identical, one and the same? We'll answer all these questions. But now, let's just try to figure out how a general way of actually doing this. And a lot of the times when you want to actually get something done, well, and this is something you're gonna, a lot of you are gonna experience in differential equations when you take it, it's gonna be a thing. Pretend that you have the answer and then kind of work backwards of what the consequences of you having the answer would actually mean. And that way you can figure out a method to get to the answer. That's what we're going to do. suppose we could express f of x as a power series, right? Which, by definition, that's what that looked like last time. Right? So suppose there was a way to get here. I have a random function, I write it as a power series. What are the consequences of that, and how can we take advantage of it? Well, that would mean, for example, that our f of x can be written as c0 plus c1 x minus x naught plus c2 x minus x naught squared plus c3 x minus x naught cubed plus c4 x minus x naught to the fourth plus dot dot dot, right? So pretend that we could do this. Let's, for the sake of argument, let's pretend we could get this done. How would we, now the question is, of course, well, the x minus x naught, those will always be there because that's what makes it a power series. It has to look like a polynomial. The only question is, how would we actually find the right coefficients to plug in? That's the actual question, right? How do I know what to pick for C0, C1, C2, C3 for any random function? So we used a method earlier today where we kind of wanted to figure out a C in a situation when we had an infinite series, and it was simply to plug in a convenient value for x. So now the question to you is, can you see a convenient value that I could plug in for x that can... Well, plugging in x equals 0 is not as great as it would seem. Because if I plug in 0 here, 0 here, 0 here, 0 here, I would have c0 plus c1 x naught plus c2 minus x naught squared plus c3 minus x naught cubed plus c... I still have an infinite series. Not great. Yeah. Alright, so a bunch of people are saying x sub 0, and that would be true. If I plug in x equals x naught, that is going to go to 0. So does this, so does this, so does this. In fact, an infinite number of terms get wiped out. Notice that f of x naught, if I plug in this point at which the power series is centered at, that will actually give me C0. So now the question is, alright, so I know what C0 has to be. It's going to be whatever the function is evaluated at this point. That's my C0. How do we find C1? Right? Now, here's the genius of the method. Here's how, and I don't know if anyone, does anyone who not actually know the answer have a really cool idea for how to get to C1? I don't know. Some of you might have seen this before. I already know C0, so I don't really even need it. Is there a way to get C1? Well, here's the traditional way to get C1, and this is, by the way, going to introduce the restrictions that we need to be able to do. Take a derivative. Now, if you take a derivative, the derivative of a constant is going to be 0, so that's actually going to kill my C1. That's going to kill my C0. The derivative of this, well, it's just a constant times this. You just take the derivative of that, which is going to be 1. That's actually going to leave you with a C1 here. Then take the derivative of that. Then take the derivative of that. Then take the derivative of that. Now, using the same kind of strategy, plug in x equals x naught. I'll wipe out an infinite number of terms, leaving me with the C1. If I take f prime of x naught, I would actually get C1. So this is the first restriction to the general method we're developing. We need to be able to differentiate the function. So it has to be a differentiable function. The limit definition of the derivative needs to exist at the point x equals x naught. So that's one restriction. How do we get to C2? Well, same idea. Differentiate again. That's going to kill the C1. I would be left with 2C2 plus 3 times 2C3 x minus x naught plus 4 times 3C4 x minus x naught squared plus dot dot dot. This means that f double prime at x naught gives me 2C2, which means that f double prime at x naught divided by 2 is equal to C2. And we continue the pattern. So, someone asked a question, I think. Yeah, so someone already thinks of us getting to the nth derivative. Boris trying to multiply redeem himself here. Yes, ultimately that's what we're going to want to build up with. But I want you guys to be able to see a pattern. So I'm going to do one more derivative and see if you guys can tell me the pattern. So if I take the third derivative, this guy's going to die. I would have 3 times 2 C3 plus 4 times 3 times 2 C4 plus, well, I would have 5 times 4 times 3 C5 x minus x naught squared dot dot dot. This would give me f triple prime evaluated at that point is going to kill all of these guys. I'm going to be left with 3 times 2C3, which means if I take f triple prime of x naught over 3 times 2, I would get C3. So, yes, as Boris suggested, we're going to want to keep doing this. We're finding the constants one at a time by just differentiating. To find the next constant, just differentiate one more time, then differentiate one more time. So the idea is, can you think of a pattern that involves the nth derivative of x naught that is somehow going to get me to any c that I want? So notice here, f of x naught gives me c0, f prime of x naught gives me c1, f double prime of x naught over 2 gives me c2, f triple prime of x naught divided by 3 times 2 gives me c3. There's a reason why I wrote it as 3 times 2 and not 6, because I wanted you guys to pick up a pattern. Can anyone pick up the pattern? What would c4 be equal to?
Fourth derivative of f of x to x sub 0 over 4 times c times 2, or the factorial form.
So the factorial form. So how can you talk about a Cn? Right, yeah, you also saw that your C4 is going to be f to the fourth derivative of x naught over 4 factorial. Because 3 times 2, well, that's 3 factorial. 2 is 2 factorial. This you can think of as being divided by 1 factorial. That's the first derivative. This you can think of divided by 0 factorial. That's the 0th derivative, right? So the original function is the 0th derivative. C sub 0 is the 0th derivative over 0 factorial. C sub 1 is the first derivative over 1 factorial. C sub 2, second derivative over 2 factorial. C sub 3, third derivative over 3 factorial. C sub 4, fourth derivative over 4 factorial. So C sub n.
That's the derivative over n factorial.
Okay, thank you, Evan. David fell asleep on us there. Okay, over n factorial. In other words, if I pretend that this was possible, a consequence of that would be the coefficients would have to follow this pattern. I can figure them out just by taking multiple derivatives. So here is what we learned. What do we learn? F can be expressed as a power series by a series where the coefficients are given by the nth derivative evaluated at the center point divided by n factorial times x minus x naught to the n. Now, of course, there are some caveats here. One, f must be infinitely differentiable to do this. Right? We have an infinite number of constants to find, and to find each constant, I need to be taking a derivative. So f must be a function that I can just repeatedly take derivatives forever. So the original constant is given by the original function. To find the first constant, I have to take the first derivative. To find the second constant, I have to take the second derivative. To find the third constant, I have to take the third derivative, and so on and so forth. So I need to be able to repeatedly differentiate something going off to infinity. So this kind of way of generating a power series can only work if a function is infinitely differentiable. So that's the first thing. One way of generating a power series is we need to be able to take derivatives. The second thing is something that was mentioned earlier. We need to make sure that we have absolute convergence here, which means we need to make sure that our derivatives are well behaved. What does well behaved mean? Well, they must be such that if I divide them by n factorial and throw that thing into the ratio test, it's going to give me a less than 1 limit. So the next caveat is f to the n of x naught must not get too large. Too large can mean, too large specifically means so that f to the n of x naught divided by n factorial does not cause divergence in the ratio test. So, assuming that we can differentiate a function infinitely often, and assuming that the derivatives don't get too big, that they overwhelm a factorial, I am able to express any function with those two properties as a power series, namely by this specific formula. And this one was there was a mathematician that came up with this formula, and it's named after him. And he kind of went through the same thought process that we just went through. Does anyone know what this is called? Oh, yeah, all right, yeah. So David just gave it. It's called a Taylor series. So it's named after a mathematician, Taylor. So this series representation is called a Taylor series. Centered at x naught. Now, there is also one special version of the Taylor series that we really like to use sometimes, and that's the one that's centered at 0. If we choose x naught equals 0 specifically, we're centered at 0 in the Taylor series. we would obtain, well, this series. F to the n evaluated at 0 specifically, divided by n factorial, times x to the n. So it's not just x minus x naught, it's x to the n. And this is called a, anyone know? Yeah, Maclaurin. I think that's spelled incorrectly, but to be fair, I always spell it incorrectly as well. Don't quote me on this, but I'm pretty sure it's spelled this way, Maclaurin with an I series. So Taylor series is a general form. It can be centered around any x value in theory, any x value that causes your derivative to be well behaved. If you specifically plug in x naught equals 0, you end up with what's called a Maclaurin series. So a Maclaurin series is just a special case of a Taylor series. And so let's just actually write. Let me recopy this just all in one place. Let f of x be an infinitely differentiable function. Now, this might not strike people as a very deep requirement, because at this point in your lives, everyone, probably the only functions you've seen have been the ones that you can differentiate as many times as you want, right? All the functions we've dealt with up to this point already have this requirement, so it might not seem like a big deal to you, but there are actually many functions that you can't differentiate infinitely often. There are some functions that you can differentiate one time, and once you differentiate it one time, you can't differentiate it again. Like, the derivative limit is never going to work out. There are some you can differentiate multiple times, but there comes a point where, oh, we're not allowed to differentiate anymore. The derivative limit is not going to work out. So it's not a requirement that a Calc 2 or a Calc 3 student is ever going to actually have to come up against, but in the real world, it is actually a valid concern. Many functions are not differentiable after a certain number of derivatives. So that's something that you'd have to worry about. We're assuming it's infinitely differentiable because we need to find the nth derivative. It's Taylor series. Centered at x naught. Is this series. F to the n evaluated at x naught divided by n factorial times x minus x naught to the n. It is a power series that would represent this function. And we're going to have to talk about how well it can actually do this. Can I think of this function as being interchangeable with its power series? The answer is not always, but a lot of the times, yeah. And that's a question of not just absolute convergence. Sometimes it's possible that this guy converges absolutely, but it doesn't converge to that function. There are times when it can converge to something else. So to be able to write f of x equals this, we actually need some more requirements, which we'll talk about next time. Or maybe the time after next, I don't remember. So that's its Taylor series centered at x naught. Its Maclaurin series is f to the nth derivative evaluated at 0 over n factorial times x to the n. provided these are convergent. So given a function, here are two methods. Well, it's really one method. This is just a special case of this. If I plug in 0 for x naught, I get that. So given a function, assuming I can differentiate it infinitely often, I can generate a power series for that function. Now, how well that power series represents the original function, can I really think of that function as an infinite sum? There's a little bit more we have to worry about when it comes to that, and we'll talk about that in a future lecture. But this is at least a naive way to generate a power series for some random function, assuming that you know how to differentiate it. And you can keep differentiating it. Is there a question? Oh, how can you tell how many times you can differentiate something in general? Well, that's actually not an easy question to answer, believe it or not. A lot of times you end up with, it's a case-by-case basis. And I'll probably give you guys some examples next time. I don't remember. There's a canonical example off the top of my head that a lot of people should know off the top of my head, but bad Jhevon. But yeah, there's no real nice answer to that. If you're the kind of person who in your line of work you're encountering functions that you can't just do calculus with them at will, chances are you're looking at some messy functions. It's not going to really be something that you can. There are classes that you can look at where you know, hey, these guys and derivatives don't mix well together. But in general, there's no real way to know unless you actually try. You're examining a function and you realize, oh, I can't differentiate this function. And so that means I can't find a Taylor series. I can probably find some other series to use here, but it's not going to be a Taylor series. And what you might do in those cases, and this is way out of our scope, is come up with a function that's almost like the function that you want to represent by a series and represent that guy with a Taylor series, but then you have to go into approximations and numerical analysis and all that good stuff. But anyway, assuming our function is infinite differentiable, we can generate these two series from it. Now, whether or not these guys converge is a whole other story, and whether or not they converge to the actual function that I used to create them is also a whole other story. We will talk about that story in the coming lecture or two. But one thing I do want you guys to consider here, let me just get out of your way, make sure you take a snapshot or copy this or whatever. At this point, let's not worry about whether these guys make sense or not. I want you to actually calculate some Taylor series for some functions. So this is how we're going to start the next class. Compute the Taylor series for these guys. Examples. Find or compute let's go with the Maclaurin series for the exponential function. Compute the Maclaurin series for the cosine function. Compute the Maclaurin series for the sine function. Earlier I mentioned an example of integrating sine of x cubed. The idea being, if I can represent sine of x as a series, that integral is actually not going to be so bad, even though it's literally impossible to do by hand. Also find their radius of convergence and their interval of convergence. So actually try to apply this formula to these functions and come up with a specific power series that you think can represent these functions. So give you some space to copy that down and get out of the way here. So you want to find a general way to talk about their nth derivative evaluated at 0, you're going to boop, plug that in right there. Question, Oh, what chapter of the textbook are we in? Someone asked. I think it's 10.7. 10.8. So power series, which we just finished, was 10.7. This is introduced in 10.8. And 10.9 is where we talk about what these guys converge to, if they can represent the function, blah, blah, blah. So we're in 10.8 right now. So we're almost done with chapter 10. I think the next class, maybe the next class with a little bit spilling into the following class, will actually complete chapter 10 and move on to chapter 11. Any other?
We don't have a class, right?
Yeah, so I think we don't.
Because CUNY has like another weird little.
Yeah, we have another shutdown thing. I have to read the fine print on that. I don't know. Do you guys want to have class anyway? I'm down to have class anyway. But I don't know if that'll be actually breaking any rules. Yeah, I was reading that earlier. I forgot the specific dates. I think there's going to be another shutdown for like 3 days, a Friday to a Wednesday, and then they're going to make spring break a little bit shorter. I was reading it earlier. I don't know, where did I put that? Maybe I was reading it in an email. But yeah, there is another
text message. The 27th to the 1st. Hello?
Yeah, hold on. Let me try to find.
Beginning this Friday, March 27th through Wednesday, April 1st.
Yeah, we're off from Friday the 27th to Wednesday, April 1st, and again from April 8th to Friday, April 10th for a condensed spring break. So they're changing spring break to go from the 8th to the 10th, and then we're taking off March 27th to April 1st.
The spring break from 8 to the 13th? No.
No, spring break is from 8 to 10.
Yeah.
You're getting like 3 days for spring break. Yeah.
So are we actually gaining back those 2 days? On the 6th and the 13th then?
I don't think so.
Because like if
Yeah.
we're gonna get those days back, then there's no point. But if we're gonna be more behind, that's dumb.
So how we get those days back is from the shortened spring break. So the days that we're off, they actually cut off a few days from spring break. Because normally spring break is like a whole week. We get like 7 days
The
off.
8th is a Wednesday, which is one of our class days.
Yeah, so.
Basically using 3 lectures.
So, yeah. I don't know. I'd have to really check that out. But I think those 3 days are for students who might need to pick up laptops and stuff like that. I think that was the thing behind that. You should all just get A's because of the headache. Yeah, unfortunately we don't give A's because of headaches. That's not how they're earned, unfortunately. Like I can't really do anything about that. You guys can appeal. You can fight for it. I won't have anything. Yeah, it kind of sucks either way. Yeah. Yeah. Well. How much time? Oh, we have like 5 minutes left. Any other questions in general? So, yeah, I don't know if I want to have class anyway and just take off the whole week or whatever. But you guys will probably have classes from other guys, so I don't even know if that's going to even make a difference.
My physics professor and English professor canceled their classes, so.
Yeah, physics specifically told us this morning, no classes.
Physics, what? Why would we pay tuition if they're canceling classes and we're not really learning?
Yeah. I know.
When will we know if we have class or not?
We can make a decision right now, I think.
Let's do it.
Of course David's down.
Yeah, of course David would be down for classes. I mean, we could, I could just do it anyway, and whoever wants to show up shows up. And the rest of you can just watch the lecture in the background, I don't know, afterwards.
I'll show up.
Yeah.
Yeah.
Yeah, I can just do it. Thanks, screw it.
I will abide by the supreme decision.
Okay. I'll send you all an email to make sure.
It's not like we're doing anything anyway.
Yeah. All right, so try doing this though for next time, which I guess is going to be Monday. Because yeah, I'm going to show up with Monday, and I also sent a link to my office hours also. So those are still working through Zoom. So if anyone of you want to talk to me one-on-one, there's always that as well. Yeah, I think I'll just continue with classes, and whoever wants to show up shows up. Because even if we get the days back, for stuff to be condensed at the end, I think overall it ends up kind of worse for you. Yeah. Yeah, I'll definitely try to get some rest in the meantime as well, but that's just a time management thing. I have to move some things around. Because I used to have horrible migraines. Now I've noticed with a weirder schedule, they're coming back. I got them under control. I'm going to try to do that again. Anyway, I think right now we're just rambling on. We can stop recording here.